When graphing a function, a good starting place is to find several ordered pairs that represent inputs and outputs for that function. For example, for this function f, we can see that when our input is 3, the output is 1. And when our input is -2, the output is -9. So let's turn these into ordered pairs and plot those ordered pairs on the graph. If we continue to find more input-output pairs and plot the resulting points, we start to notice that all the points that we've plotted so far fall in a straight line. In fact, no matter how long we continue this process, every point that we find for this function would fall on the same line. And if we were able to find and plot an infinite number of points, eventually, all the gaps between the points would go away, and we would see that the result is a solid line. These are the principles that will guide us through this video as we graph linear functions. Even though lines are inherently made of an infinite number of points, it can be a bit laborious to think of them that way. If we tried to create every graph by plotting an infinite number of points, we would be plotting, well, forever. Thankfully, though, there's a much easier way to represent this infinite number of points. We simply draw a line with the understanding that every point on that line is a solution to our equation. Then, the main issue that we face is knowing where to draw a line for any particular function. To know where to draw a line, we technically only need to know 2 points on that line. But to make things a bit more robust, let's take 5 points into consideration. Suppose we have the function f of x equals x. This is the most basic linear function, called the parent function, and evaluating this function is simple. Whatever the input is, the output is the same number. So let's pick our inputs to be the integers from -2 to 2. And since our outputs will be the same as our inputs, we can simply repeat our input numbers in the output column. Then, we can plot our points, and once we confirm that all our points fall on a straight line, we can draw the line that connects all those points to represent our function. Now let's repeat those steps for a slightly more complex function. Suppose g of x is equal to 3x minus 1. For our inputs, we are once again going to use the integers from -2 to 2. But this time, the process of finding our outputs will be a bit more complicated. So let's take a moment to show the calculation needed to find each output value. Once we have our output values, though, the graphing process is the same. We plot each point from our table, confirm that the points fall in a straight line, and draw the line that connects the points. And for one more example of this process, let's take a look at the function h of x equals -x plus 7. The biggest difference with this function is that x needs to be negated before we add 7. This results in our outputs decreasing as the inputs increase, which in turn leads to a line that goes down as we move from left to right. Of all the example lines that we have graphed so far, one aspect of linear functions has been missing: division. So let's shift gears a bit and consider some linear functions that contain division, starting with f of x equals x divided by 3 minus 4. Up to this point, we've been choosing these 5 numbers as our inputs. So let's continue that trend and see how it goes. As we evaluate the function for each of these inputs, you may get a bit annoyed that we have to do so many operations with fractions. And while there's nothing inherently wrong with having fractions as our outputs, these values can lead to a bit of imprecision, especially if we're graphing by hand. So instead of choosing these 5 input values, let's see if we can modify our inputs to make our lives a bit easier. First of all, notice that when we plugged 0 into our function, we didn't have to deal with any fractions, since 0 divided by 3 was an integer. The trick then is to see if we can find other input values that have this same property. And if we tried a variety of input values in this situation, it wouldn't take long for us to discover that any multiple of 3 is going to yield an integer output. So let's adjust our table of values so that the inputs are only multiples of 3. We'll keep 0 around, but then we'll jump to 3 and then to 6. And to keep things balanced, we'll also include -3 and -6. Now when we evaluate the function for each of these inputs, our calculations go much smoother. Additionally, when we graph these points, they also give us a broader picture of what's going on with the function. Instead of getting points that are tightly clumped around the axis, we get points that are spread out a bit more. For our next function, let's consider g of x equals -3/5 x plus 2. While this may look slightly different from our last function, with a bit of rearranging, we can rewrite the function to emphasize that x is being divided by 5. Then, similar to our last function, the 5 in the denominator here has the potential to give us lots of fractions in our table of values. However, if we're clever with the input values that we choose, we can once again avoid most of the fractions. And since we're dividing by 5 here, let's choose input values that are easily divisible by 5. Now, when we calculate our outputs, we end up with integers, which makes this easy to graph. While we could move on to our next function at this point, there's one special property of the inputs that we chose here that's worth exploring further. And in order to see this special property, we're going to make an extended table of values. So consider the function after we rewrote it. Then, for our extended table of values, we're going to include the following columns. As we fill in the table, there might be one column in particular that jumps out at you. Notice that after we divide each of our inputs by 5, we get the integers from -2 to 2. These were the 5 values that we used as inputs earlier in this video, and even though we eventually stepped away from using them as inputs, they still made an appearance in our problem-solving process. Now let's consider another function that contains division. h of x equals x minus 1 over 4 plus 5. And like last time, let's make an extended table of values to show the process of getting from our inputs to our outputs. Also like last time, we're hoping that one of our columns in the extended table of values will contain those 5 key values from -2 to 2. However, instead of just hoping for this, let's build our table around this concept. Let's make it so that after we take the step of dividing by 4, our values end up being the integers from -2 to 2. Once we fill those values in, we can see that we need to complete the table in 2 directions. We need to make our way to the left to figure out what the inputs should be, and we need to make our way to the right to determine the final outputs. Making our way to the right is pretty simple. Since we already know what x minus 1 divided by 4 is, we just need to add 5 to each of these values to determine the final outputs. It's the other direction that'll be a bit more challenging. But as long as we take things one step at a time, we should be able to figure this out. So for now, let's just focus on these 2 columns. From the second column to the third column, the key change happening is that we're dividing by 4. So our goal is to figure out what numbers should have been in the second column before we divided by 4. Well, that sounds like a job for inverse operations, which means that when we work our way backwards, we need to do the opposite of dividing by 4. So let's take our numbers from the third column and multiply them by 4, which gives us the values that belong in the second column. The same concept can be applied to figure out the numbers that belong in the first column. We know that after subtracting 1, we got the values in the second column, so if we add 1 to the values from the second column, we'll get the input values that belong in the first column. And from there, we can graph our points and draw our line. Now, this strategy for finding inputs and outputs may seem like a bit of overkill for a linear function, and honestly, it is. There are other strategies for graphing lines, like plotting the y-intercept and using the slope to find a second point, that will work just as well and probably get you your answer faster. However, this video series will be exploring many other types of functions, and the skills needed to graph lines using simple strategies won't typically translate well to other types of functions. But the idea of key values and meaningful inputs is a concept that can be applied to a wide variety of functions and help develop a deeper understanding of those functions. That concludes this video on graphing linear functions. Hope you learned something new, and thanks for watching.